Alright, welcome to the first lab. This is our introduction to ANSYS Mechanical. We're going to be doing a 2D gear and rack analysis. And what this lab basically consists of is a two-part assembly that has a spur and rack gear. And they're basically components from a 2500 Newton hand press. We're going to be solving it in 2 dimensions where our model is drawn in 2 dimensions and we specify a thickness in the 3rd dimension. What we want to do is design a press that's capable of delivering 2500 newtons of force in the rack. But in order to do this, we have to determine the required torque in the gear to produce that force. So we'll apply the desired force in the rack and extract the moment at the reaction gear. So we're basically doing this backwards. We know what we want to come out, and we'll determine what it takes in the gear torque-wise to get that reaction force. So we're going to be using a remote displacement to constrain the gear. Basically what this is that it allows us to specify which axes are fixed and which axes are not, compared to a fixed support where everything would just be stationary. So that allows for rotation in addition to translation constraints. This becomes important, especially in later simulations you'll be doing for your actual senior design projects, which is the reason why we cover this in this lab. So, a brief overview. We're going to be doing a simplified 2D simulation and then set a thickness to give it 3D. We're going to define how the rack and gear are in contact, then define the gear to rotate about a point in space. Then we'll specify how the rack is fixed in space, and you'll apply a force to the model. So to begin, you should start by downloading everything from the Blackboard website. So you'll see that there are step files there, as well as a PDF with these same instructions. Now if you look at my mouse, you'll see that this is what my left click looks like. You see there's a circle around it. And the right click is a different colored circle appearing around the mouse button. So just be familiar with that so you can see how I'm clicking. And you can track my mouse. I'll be talking about specific things around the mouse location as we move through the lab. So to begin, we start in our project schematic screen, okay? And we have to go into the toolbox, which is here on the left side, and specify an analysis system. For this, we'll be using static structural. So double click on static structural, and the module will appear inside of the project schematic. So I'm going to name this one tutorial. Now the way that this is organized is literally you go step by step and fill everything out. So in the beginning you have engineering data. We're not going to cover that yet in this lab. Then you have to set up the geometry, set up the model, set up the problem, get the solution, and then look at the results. So this is your step by step and you just pace through it. So our first step will be to specify that this is a 2D problem. In order to do that, you will click on geometry, right click, and select properties. Now you should have a properties window show up on the right hand side here, just like mine. In this window, on line 19, you will see that the analysis type defaults to 3D. However, we will be doing a 2D simulation, so you should click 2D. You can only set this before you import your geometry. Once you import your geometry, it will not allow you to change it, so be sure to do this step right now as the very first step. Now we'll click out of that screen. The next step will be to actually import your geometry. So I specify it for you and give it to you in this lab. What you can do is right click geometry, import your geometry, go to browse. You'll see that I made myself a nice folder here, lab 2 part 1, where I put the gearset2d.stp, which is a step file. You can then open it. And then you'll notice that this now turned into a check mark. So your geometry is set. The next thing that we're going to do is double click on model. This will actually open up the ANSYS mechanical screen. You'll notice in the bottom left it says starting mechanical, so we just have to wait a moment. There it goes. Alright, so now we have mechanical. You'll recognize a lot of these buttons from the earlier lab where it showed you where everything was inside of ANSYS. Now on the left side we have the project tree, and once again, just like before, this is just something that you step through one by one. And what you'll notice is that everything that's done so far has check marks. Everything that needs to be updated has a lightning bolt, and things that you have not set yet have a question mark next to them. So you have to ensure that everything has check marks before you actually run your simulation. So the first thing that I'm going to do, and this is a very good practice in ANSYS, is go to units and specify your units. For this problem, I'm going to be using millimeters, kilograms, newtons, seconds, millivolts, milliamps. Okay, so set it to this. You may see that your ANSYS can default to something else depending on the last person that used it. So always check that your units are correct. So I'll click on millimeters. Once we've done this, then we'll move into the geometry branch. And we want to expand it by hitting the plus. Now here you will see our gear and rack. Alright. What we're going to do first is inside of geometry and verify that our 2D behavior is plane stress behavior. If you have anything other than this, make sure that you change it to plane stress. Alright. Once we have that done, we then click and shift click the gear and rack to highlight both of them. Now what we want to do here is specify the thickness. So we will specify it as 12 millimeters according to the lab. There are some other things here that you can take a look at. For example, the material is set to structural steel. We'll leave this as structural steel. We do have nonlinear and thermal effects. We have flexible stiffness. And there's more information in here, so feel free to explore. We will not be changing any of this from the defaults in the lab. Now also make sure that you do not have the thickness box checked. Alright? If you do, the lab will come out wrong. The next step will be to actually set the contact options. So we will go into connections and expand it. This is where you'll see contacts. Expand this and you'll see contact region. So we'll click on the contact region, and this will show you where the gear is in contact with the rack. And you see here specifically that these are the gear contact faces, the red lines right there, and the blue lines are the rack contact regions. Now if we go through this geometry selection, we'll see that the gear is in contact with the rack. Now, one thing that we want to change here is that the definition of type is currently bonded. So these are actually bonded together as if they were glued. This is incorrect for our simulation. And we want to set it to no separation. So we want to keep these faces in constant contact, and we do not want them to separate, but we do not want them to actually be, fixed together at that specific location. So our next step will be to go back to the geometry and then go up here to the top ribbon and use the edge selection tool. So you'll notice that there's a vertex, edge, face, body. We want to select an edge. You will click on this edge, which should be highlighted green. You will then click up on model and right click on the edge to insert a remote point. And your remote point should be inserted in the center of this edge. Now in the case that it's not, you can just go back to geometry here and click it, and then re-click the edge and hit apply, and now it should be selected. Alright, then your next step will be to insert your remote displacement. So in order to do this, we will go back to the static structural branch down here, right click, insert, remote displacement. Alright, so now we have a remote displacement boundary condition. Your first step will be to change your scoping method from geometry selection to a remote point, and then from remote points select the remote point we just created. Then you see that our X, Y, and rotational Z components are all free, meaning that all of this can move. What we're going to do is specify that they are 0. So now our X, Y, and rotational Z components are all set to 0, remote displacement. So now we have a gear with a remote point inside of it from this edge that has a remote displacement fixed at 0 in X, Y, and rotational Z components. So the next step will be to add a boundary condition to the rack that will allow it to slide up and down without friction, so it doesn't bind. In order to do this, we go back to static structural, we click insert, frictionless support. Now the frictionless support will be applied at this back edge. So you'll go here to geometry, you'll see there's no selection, click on it, and click on this edge. Once you've clicked on the edge, you can hit apply, and you'll see that this one edge in blue has a frictionless support applied to it. If it's trying to select something else, make sure that you have edge selection turned on. So now the next step will be to apply the actual force to the model. So we'll apply the force here at the bottom. I'll just right click on this bottom and insert a force. And you see that a force appears here in static structural. And it needs a geometry. So my first step will be to click this bottom and hit apply. And then you see that it's highlighted in red, that this geometry will have a force applied to it. And it wants us to input a magnitude. Well, we don't want to do this by terms of vector. We want to do this in terms of components. So now you see that we have an X component and Y component. So we'll specify that our X component force is 0 and our Y component force is 2,500 newtons based on the problem statement. So we have a Y component force of 2,500 newtons pushing up on the rack. We have a frictionless support, so I'm going to click here. We have a frictionless support here, B, on the right side that just guides this rack. And then we have a rotation about A in the gear. Alright? So we'll generate a very basic mesh for this as the next step. You can go here into mesh, and you see that there are many options. For example, sizing. So we have a coarse relevance center with a coarse span angle center with our minimum and maximum element sizes set to default with a default growth rate and so on. So what we're going to do is just right click on mesh and hit generate mesh. Now you can see that it's generated the default mesh. If we wanted to make this mesh finer or coarser, the quickest way to do it is through relevance. If you click in here, there's a slider that appears that can make the mesh finer, so finer to the right, coarser to the left. So if I set the relevance to 100, you don't have to do this step, by the way, and then go to generate the mesh, you will see here that all of these cells get much smaller. Just give it a moment. You see how the cells became much smaller and the mesh is much finer? Similarly, if we slide this all the way to -100 and then right click to generate the mesh, you will see that it gets much coarser, all of the elements get bigger, and our solution will actually become less accurate. It becomes a delicate balance of how much mesh should you have. But for this problem, we're just going to set it at 0 and then generate our mesh. So we're using the default mesh with all of the default sizing for this example. The next step will be to simply solve the model. So there's two ways to do this. The first one is to go up here into the ribbon and you'll see that you have solve, which you can click and this will solve your model. The other way, and the way that I prefer to do it, is right click on the solution and hit solve. So this will actually go and solve our problem. Now you see that a warning pops up that not enough constraints appear to be applied to prevent rigid body motion. This is expected for the way that this problem is set up. If you have different messages appear here, then something has been set up wrong. Okay. But now you'll notice that we don't actually have any results. So in order to get some meaningful information from ANSYS, we have to tell it what we want. The first step that we're going to do is look at the deformation. So if you go to Solution and right click it, you can insert deformation total. So this will show us the total deformation. Then you just need to click on it or right click on it and evaluate all results. And here you go. This is the total deformation of our body, which you will see it agrees with the PowerPoint presentation which I've given you guys. Another thing that we can do, and what we actually care about for all of this, is to go into the solution, right click, then insert our probe, and the probe will be a moment reaction. Alright, because this is what we're interested in, is the moment about the center of the gear, or the torque. So you'll see that we want to do this based on a boundary condition. I want to know the moment about the remote displacement that I placed in the middle here. Alright, I'm not interested in the moment on the frictionless support because that'll tell me nothing. So I'll select the remote displacement. Okay. Now we go back to the solution and evaluate all results. Then click back on the moment reaction and you see right here the torque. So our total maximum value of torque is 92,234 Newton millimeters. So this is the torque required to generate a reaction force of 2,500 newtons on the bottom of our rack, which is the solution to our example problem here. Now, I'm going to show you a couple of extra things here to make this useful for you. So you can also insert other information here. For example, one very, very useful thing is the stress tool. So for example, you can do maximum equivalent stress, which you can then evaluate. And here you'll have something that you guys probably all recognize, the safety factor. Now you see here that your minimum safety factor in this design is 2.1536. Isn't that useful information? Similarly, you can do other things like stress, for example, von Mises stress, and update this. And then you'll actually see the stresses inside of the gear, on the teeth, and so on. And you can keep going. There's a lot of very useful information in here. Alright. So this is basically the end of the tutorial for this lab. I believe it was very short and sweet. In your assignment, you will be looking for a target maximum reaction force. So all you need to do is figure out which one of these steps you have to change to hit that new target that I gave you. Now let me give you a quick hint for this. So I will close mechanical here. You will notice that now everything has checkboxes in Workbench. In order to prevent you from overwriting all the work you've done up to this point, what I recommend that you do is click on this left arrow here and duplicate. So it's copying all the work we've done up to this point. So now once it's copied the tutorial, we can simply name this homework. And this is a duplicate of all the work we performed up to this point. And if you double click here in setup, you'll see it launch mechanical. Let's give it a moment because it's starting mechanical, as you can see. And this is an exact copy of everything we did up to this point. So you see the remote displacement, the frictional support force, everything. Alright. However, you'll notice these lightning bolts, meaning that it needs to be updated. So I'm just going to go up here and update the project. So this will just update all of the steps so that this solution is the same as the tutorial solution. And you see it's going step by step. So setup is now checked, solution is now checked, and results will be checked in a moment. There we go. Now it'll start mechanical again since I double clicked on results. Give it a moment. And here we have the exact same results as before. Now it's up to you to figure out what you need to change here in order to yield the homework solution for this lab, which you will type up. Once you are done, or at any point during this, you can simply save your project. So I will save my project since I have to give this to the TAs inside of my folder, and I'll just call this lab 2 P1. In the case that you plan on moving this between machines, rather than doing a simple save as, you should create an archive. But what the archive does is creates a zip file with all of this information in a single file. You'll notice that after you save your project, there is a directory structure that's created. And this directory structure actually has different information scattered about. So if you simply move your Workbench project file, the WBPJ file, you will not have all of the information necessary to view the results and everything. So I recommend creating the archive. Alright, that's the end. Time to do the homework.